All right, so here's now the second part of this video where we're going to go back to the special 45-90 triangle, my 1, rad 2. We're going to talk about sine, cosine, and tangent, and we're now going to find the sine of 45, the cosine of 45, and the tangent of 45. So the sine, according to SOHCAHTOA, is opposite side. So opposite has to go all the way across the triangle. So the opposite side is 1, and it's going to the hypotenuse, and the hypotenuse is always opposite the 90 degrees. So here's my right angle, my 90 degrees. This guy is my hypotenuse. Hypotenuse, if you recall, is also the longest side of the triangle. So we get 1 over rad 2. Now, if you remember when we did the radical unit, I never wanted a radical in the denominator. It was a really big deal. And now we're at that point where you really have to be able to get that radical out of the denominator. If it's a monomial in the denominator, we simply square the denominator. So this is a monomial, single term. I'm going to square it. Now, I'm not going to just write an exponent, because if I do that, I might confuse myself. Let's write it out. Rad 2 times rad 2 means rad 2 squared, which gives me 2. Now, whatever I do to the bottom, I better do to the top. 1 times rad 2, I get rad 2 over 2. The sine of 45 is radical 2 over 2. That's an exact value. Do not think you're going to type this in on your calculator and give me decimals. You can't. You have to give me exact values, and exact values would be in radical form or fraction form. So that's another reason why this whole year I've been going crazy about don't give me the decimal, give me the fraction, give me the radical. Now we're at the point where it really, really matters. So I hope I got that locked into your brains. So now we're going to do cosine. Cosine is the adjacent to the hypotenuse. Well, look at it, it's the same thing. So the cosine is rad 2 over 2. So the sine of 45, cosine of 45 are the same way they have the legs that are the same. Now the tangent is equal to the opposite over the adjacent, 1 over 1, the tangent of 45 is 1 whole. Now this is going to work no matter what side triangle they give you. Just to show you a different example, if I gave you a triangle and it's a 45-90, there's my 45-90, I tell you a leg is 3. Well, once I know one of the legs of an isosceles triangle is 3, I know the other leg is 3. And here's the thing. This will now be 3 rad 2. Now, don't believe me? Practice on the unit circle. You're going to get back to the same ratio that we have here. And if I were to now find the sine of the 45 using these numbers, I have opposite to the hypotenuse. This would be 3 over 3 rad 2. Well, the 3's canceled. So now I have 1 over rad 2. Rationalize this guy out. And I have rad 2 over 2. So it's special because if you know this, you know it no matter what lengths they give you. If it's isosceles, it's going to always reduce down, and you will have rad 2 over 2 for sine and cosine and 1 for tangent. So that's the first important special triangle, the isosceles triangle. Now we have to talk about the other very important special right triangle, and that would be the 30-60-90 triangle. Okay, so now we're going to go to special triangle number 2. So now special triangle number 2 is the 30-60-90 right triangle. So here we draw ourselves a little picture. It's not isosceles, so we have to make sure that we do have one side longer than another. And I always label like this because it helps me to always get it right. And students who do this usually get it right. Start your labeling at your 30 degrees. Here's 30, here's 60, here's 90. And then you're going to go, so since I labeled my angles going clockwise, now my numbers for the sides I will label counterclockwise. So again, I go 30, 60, 90, and then I go 1, 2, rad 3. 3, 6, 9, 1, 2, 3 with the radical. Now, why is this so important? Well, it's important because, one, this works with the Pythagorean theorem. If I have my a squared plus b squared equals c squared, my altitude here is rad 3, which is going to be squared. My base is 1, which is going to be squared. And does this make my hypotenuse, which is 2 squared? Well, you square a radical, the 3 drops down. 3 plus 1 equals 4. These numbers will always work. This is the base number for a 30, 60, 90. You have a 30, 60, 90 with any other numbers, your sine, cosine, tangents will always reduce back to these. So let's first look at the sine, cosine, tangent of these, and then we'll look at another one. So if I now take the sine of, let's go with the 30 degrees first. Now this is the angle I'm looking at, not the 60. So the 30, everything is from the 30's point of view, the 30's perspective. Opposite would be the 1. So sine again would be opposite over the hypotenuse, which will never change. That's always opposite the 90 degrees. You get 1/2. The sine at 30 degrees is always in a 1:2 ratio with opposite and hypotenuse. This 1:2 ratio is a pretty important ratio. The side opposite 30 degrees is always in a 1:2 ratio with the hypotenuse. Now, if I wanted the cosine of 30 degrees, again, I'm always from the 30. Here's my adjacent. Again, like I said on the other video, adjacent is always going to connect the angle and the hypotenuse. So this would now be rad 3 over 2. And the tangent of 30 is going to be my opposite to my adjacent, which is 1 over rad 3. So now I have to rationalize. I can't have a rad 3. So the tangent of 30, rad 3 over 3. Again, like I said, it does not matter what other numbers they give you. If this was a 6, this would have been 12, and this would have been 6 rad 3, which we'll look at again. So as long as the side opposite the 30 to the hypotenuse is in a 1:2 ratio, you could figure out the other side by whatever the opposite side is multiplied by radical 3. Let's take a look at the 60 degree angle. I'll use red now. If I wanted the sine of the 60 degrees, well, here's my 60. Now, the opposite side is rad 3 because now I'm going from 60's perspective. So my opposite is rad 3, still the same hypotenuse. My cosine of 60 is now my adjacent. So now look at my 1 is my adjacent to my hypotenuse. And here's my 1/2. And my tangent of 60 is going to be opposite rad 3 over adjacent 1. Rad 3 over 1 is rad 3. I want you to notice, very, very important to please make note. In the same triangle, 30 degrees and 60 degrees add up to 90. If you remember back in middle school, and I think in Algebra 1 too, they would be called complementary angles. Two angles that add up to 90 are complementary. Now, when you have two angles that add up to 90 in the same circle, they're called, the sine and the cosine then would be called cofunctions of one another. And the cofunctions, if you look, the sine of 30 to its cofunction, cosine of 60, they're the same. The cosine of 30 to its cofunction, the sine of 60, they're the same. So let's write down a little something about cofunctions. Hopefully you have that all written down. I know this is a lot, which is why the videos will be here for you. Anytime you need to look back, you should find the video and rewatch so that all these little details really become part of the way you think. So cofunctions. Cofunctions. Cofunctions are two angles in the same triangle whose sum is 90 degrees, then the sine of A would equal the cosine of angle B, and the cosine of angle A would equal the sine of angle B. So again, if we wrote a 30, 60, 90, and let's say you get a triangle starting from the bottom. Here's your 30, here's your 60, here's your 90. Then again, if I went counterclockwise labeling the angles, I'm going to go 1, 2, 3 with the radical. So one way angle, the other way the numbers. You'll always get the numbers on right. If I call this angle A, and I call this angle B, and I call the 90 degrees angle C, the sine from angle A is 1 to 2. And then the cosine of B, 60 degrees, would be adjacent to the hypotenuse. Always going to work, cofunctions. If I took the cosine of angle A, here's A again, cosine adjacent to the hypotenuse. This is going to equal the sine from angle B. Here's B, the sine adjacent to the hypotenuse. So cofunctions, really, really important. Hence the name sine and cosine. It's all connected. So these are my special right triangles. And why are they so important? Well, we got to get back now to the unit circle. So the unit circle, where we were going with this all along, we need a nice neat triangle, set of axes. So here's my positive y and my negative y, and here is my positive x and my negative x. I'm labeling with the letters as well as the numbers. So this is pretty important stuff. My positive x-axis is my 0 degrees and my 360 degrees. My positive y-axis is my 90 degrees. My negative x-axis is my 180 degrees. and my negative y is my 270 degrees. Now, the unit circle, unit means the number 1. So let's write that down. Unit means 1. So therefore, on the unit circle, my radius is 1. That's not the leg. Now on the special 4590, my leg was 1. But now my radius equals 1. So if I now had a 45-degree angle drawn on the unit circle, so here's my 45 degrees, it's a quadrant 1, and my radius is 1, then this means that on the x-axis, this base is actually the length of how long I came out on the x-axis. It is actually, the base is the x-coordinate. And however high I went up, this is now my altitude. And this is equal to my, I better get a better marker, this altitude is equal to my y coordinate. And if I'm on the unit circle, this point P that I just made, which would come from the x coordinate and the y coordinate, now let's talk about how it relates to the Pythagorean theorem. Well, if I had a 45-90 triangle, which is now what I have, the two sides, the altitude and the base, are equal to one another. The radius is 1. So if I use my calculator, which I'm going to need a decimal just for the purposes of the video, I'm going to use a decimal and I'm going to use a radical if necessary. So here, if I take my a squared plus b squared equals c squared, the radius is 1. The radius is the same as the hypotenuse. This is 1 squared. The base and the altitude, I don't know what they are, so I am just going to call them both, for right now, x. Because I don't know how long this is and I don't know how long this is. Well, x squared and x squared, or 2x squared, is equal to 1 squared is 1. And divide by 2, I get x squared is equal to 0.5, terminating decimal. So right now I'm just going to leave it at that. And if I were to now take the square root, so now I have the square root of 0.5, I get 0.70710678812. And just for argument's sake right now, I'm going to say that this x is roughly, not equal, roughly 0.71. So that means this base, I had to come out to this point here, which is 0.71, comma 0 for y. And then I had to go up. How high did I go up on the axis? I went up to 0.71. This y coordinate would be, if I plotted the point, 0.710. Now this point P, if I took both of these together, this point P is 0.71, comma 0.71. It's a little confusing, I know, but if you try to follow along, the base is going to be equal to, I'm going to get rid of the word base, the base is equal to the cosine of x, and the altitude would be equal to the sine of x, and that would be the x coordinate and the y coordinate. Now, if we were to check this out on our calculator, and I wanted the sine, which would be y, of 45 degrees, and the cosine, which would be the x, of 45 degrees, and now I'm in degrees, so here's where you have to hit the word mode on your calculator, and you have to go down and make sure you're in degree mode. So make sure you're in degrees. And quit out of there. So if I put the sine of 45 degrees and I hit enter, look I get the exact same number I got when I used the Pythagorean theorem. And if I did the cosine of 45 degrees, enter, I get the same thing. So it's kind of neat. The tie-in is really, really, really neat. Now, so this would be 0.71 and 0.71. Now, it doesn't matter where I put my 45 degrees. So here's where now that reference angle is going to come into play. So we're going to do all about the 45 before we go into the 30, 60, 90. So now if I get rid of this, and I'm going to write it again a little bit neater. So let's put my y-axis back in and my x-axis back in. If I went beyond 90 degrees and I went into this second quadrant and I gave myself a 45-degree reference angle. See, now this is the angle that I drew. So if I wanted to know what angle I drew, this is a 135-degree angle. So if I take a look at this and I say, okay, let's find the sine of 135 degrees. The sine of 135 degrees is equal to the sine of 45-degree reference angle in quadrant 2. And the decimal version of the sine of 45 degrees would be roughly 0.71. But if I wanted it to be the exact, then I would go back to labeling 1, 1, rad 2. This decimal here, 0.71, would also be the same as the sine of 45, which would be rad 2 over 2 from the other video. And they're all connected together. Now, so this would be, again, the sine of 135 is equal to the sine of 45 in quadrant 2, which would be positive 0.71 or rad 2 over 2. But what about the cosine of 135 degrees? Well, cosine is equal to, as we just said, the x coordinate. So cosine, let's write ourselves a note. This is the x coordinate. And the x coordinate in quadrant 2, here's quadrant 2, it's negative. So the cosine of 135 degrees is equal to negative cosine of 45 degrees in quadrant 2. See, now you got to pay attention to the sign of your axis. Is it positive? Is it negative? It's super important. And so then this would end up being negative 0.71 in decimal form, or it would be negative rad 2 over 2 in exact value form. If we were to then, and I'm going to use a different color, if we were to want to know, what about if I had an angle that went all the way around like this and gave me a 45-degree reference angle in quadrant 3? Well, if I have a 45-degree reference angle in quadrant 3, that means it came from a big angle, which was 225. So if I started out asking you, what is the sine of 225 degrees? Well, this would be equal to the sine of 45 degrees in quadrant 3. So here's my reference angle. Now let's take a look. Now sine is the y-coordinate. When I'm in quadrant 3, my y-coordinate's negative. That means my sine of 225 is going to be negative because of the coordinate. So then this would be negative rad 2 over 2, or negative. And if I wanted the cosine of 225, this would then be negative cosine of 45 in quadrant 3. Again, because the x-coordinate is negative. So if they ask for the decimal or they ask for exact value, you got to pay attention to the directions. And now let's talk about quadrant 4. I'm going to erase this stuff so I can fit quadrant 4 neatly. Hopefully you are taking notes, or you'll just, bookmark this video so you can go back to it. And I'm going to do the 30, 60, 90 on a new video so the videos aren't too big. So now if I were to draw this angle, which is 315 degrees, 315 degrees terminates in quadrant 4. And 315 degrees gives me a reference to my 360 as a 45-degree angle in quadrant 4. So if I wanted the sine of 315 degrees, this is equal to the sine of 45 in quadrant 4. Now again, sine is the y-coordinate. Y-coordinate's negative in quadrant 4, so this would be negative. So the sine of 315 would be negative rad 2 over 2, or negative 0.71. But the cosine in quadrant 4 is the x-coordinates. Let's just write this. The cosine of 315 degrees is equal to the cosine of the reference, 45 degrees, in quadrant 4. And in quadrant 4, the x-coordinate is positive, so this is positive. So this would be positive rad 2 over 2. The thing is it matters where you land. Where's your 45 degree? Is it in quadrant 1? It's positive for x and positive for y. In quadrant 2, it's positive for y, negative for x. Quadrant 3, negative for both x and y. And quadrant 4, it's positive for x and negative for y, which brings us to this little acronym. And this acronym says, all students take calculus. So what this means is in quadrant 1, all functions are positive. So A means all functions are positive. In quadrant 2, here's my positive y, my 90 degrees, and my negative x, my 180 degrees. S is the only guy in quadrant 2. This means only sine is positive. That means cosine and tangent would be negative in quadrant 2. I come around to quadrant 3. And again, let me just get rid of some of this stuff so it's not so sloppy. So if I come around to quadrant 3 comes from negative x and negative y. That means cosine's negative, sine is negative, only tangent is positive in quadrant 3 because of a double negative. Only tangent is positive. And then quadrant 4, only cosine is positive. Because it's positive x, sine is negative, tangent would be negative. So I'm going to stop this video here. Please make sure you understand all the things. Email me things you don't understand. And in the next video, I'm going to talk all about the 30, 60, 90 on the unit circle.